Speaker is Thorsten Liebig. He is a co-founder and one of the co-owners, I believe, of Derivo. Did I say that correctly? Yes. And his presentation is going to be connecting the dots of linked data of resource collections. And put this up.
Okay, let's see.
Great.
Okay. Good morning, everybody. My talk is about connecting the dots of linked data of large resource collections, and I think there is evidence enough that linked data is a successful technology for storing and managing large resource collections in the library domain. We just have to look at the abstracts of today and tomorrow, and that's something which really is a hard thing to do, to convert data from distributed sources, different formats, into one consistent knowledge graph, I would say. I know that from our own projects in industry, and I appreciate a lot that you're doing this hard work. But in my presentation, I will not talk about data ingestions, rather than how to query, how to visualize, and how to show this data to potential users, and hopefully in a way that makes sense to them. And I will give some presentations. Before I start, some background on myself. So I'm part of a team at derivo that does applied research and solution development in exactly the area of semantic technology. So we help companies and organizations in facing the challenge of more and more distributed, heterogeneous, and large data sources by a semantic management of that data. And we have also done projects or contributed to community efforts such as the O-link protocol. So we have been in charge of specifying this protocol, which basically enables applications to speak literally OWL and to transfer queries. And that protocol became a W3C member submission some years ago. And we have regularly contributed to the OWL API, the most prominent Java API for dealing with OWL ontologies. Our main customers are in the engineering domain. We have projects with Siemens, Schaeffler, and others. And there we typically help these clients to build large knowledge or enterprise graphs. So what they're curious about currently is to build kind of what they call digital twin of their complex systems or products. That's basically a digital copy of all the information and knowledge about their systems, which is required to build, operate, and maintain those complex systems. We have also done some projects more in the area of this conference. So we have been participating to or been involved in a proof of concept for the American Art Collaborative. That was a project that tried to gather linked data for 14 large American art museums, and we were in charge of building a visualization of this linked open data pool. And we are a key partner of Springer Nature in their SciGraph linked open data initiative. SciGraph is an initiative of Springer Nature to publish all the metadata for all of their articles, authors, patents, journals, grants, and so on, from today back to the first publications in 1830, I think. So what's in an REF graph? So almost all presentations or projects presented in today and tomorrow deal in some sense with graph technology, and most notably the REF graph model. And the good thing about REF graphs is that it represents the simplest possible structure you can have to build a graph. So it's just a triple statement. You have a resource that relates something else, another resource are literal by a property, and that's a statement. And that's very nice because because it allows to easily produce, exchange and consume this kind of data. There are different syntaxes, but if you break them down, it's basically just a triple statement. And that makes it easy to build a straightforward query language such as SPARQL, because there you just have this triple query patterns, and it's kind of easy to directly query your data, as opposed to complex SQL queries, for instance. It has a downside in my understanding, because everything also has to be a triple. So if you would like to attribute such a statement, you have to make something like reification to introduce new blank nodes and a couple of new statements that blows up your data in a way. It's a technical thing, but in the end, you have to deal with that when you do querying, for instance. And another thing is that you mix up schema and data in an REF graph. So there are some triples that are data about the data, kind of metadata for your data, like type information or your class hierarchy or whatever. But that's mixed up with your ordinary data, I would say, and on a syntactic level, you cannot distinguish which is one. Is it schema data, or is it the data you're talking about? And let me elaborate on this a little bit to understand how this affects building queries and exploring REF graphs. So here's a simple example of an REF graph. Think of the labels for the nodes as being the IRIs for these nodes, and the labels on the edges as being the IRIs of the properties. And the real data you're talking about in this graph is that which is here colored in orange now. So there are people like Sandra and Mike, and they have family relationships in between them. But if somebody asks you what's in your graph, you typically would use the schema terms. You say, okay, I have persons in my graph, and some of them are females, others are male, and they are related by the has, son, or other family relationship. So there is, in my understanding, kind of, or should be a strong distinction between the schema and the data itself. So that's the graph on the left-hand side that represents schema information, and the subclass relationship is on a other qualitative level than the age or is sibling relationship. But what we more think about this is that we type our nodes in the graph by the class information we have in the schema. So the schema, or called T-box in the ontology domain, is the vocabulary of your domain, and this vocabulary also includes the relationships, and these relationships can also be in an inclusion relationship. So he has son is a relative relationship, and that's what we typically do at customer side, that we build the model together with domain experts and to introduce new levels of abstraction to the model. And there's the age relationship, and that's kind of a special relationship. So it's a relationship that refers to a literal, in this case, a number. In a labeled property graph model, this wouldn't be a relationship. It would be just an attribute of your node, which is kind of cleaner in my understanding if you just look at the data. And what we typically do is that we try to make the data conform to the schema vocabulary. So there should never be an age edge between two resources in your data, because that's the relationship that adds a link between a node and an integer. So your triple store typically does not complain if you give them those kind of triples. They don't care. They're not typically not schema aware, but in my understanding, that's really something which we should take care of, that the data really is conforming to the schema. It doesn't use types or relationships which are not introduced at some point in the schema. And the good thing about REF, or the languages which are on top of REF, such as OWL, is that you can encode knowledge about the domain. So I just give you two simple examples. I think you all are aware of what's able with OWL. So if we declare the is-sibling relationship as symmetric, then we implicitly get all the other relationships between two-person nodes, which are siblings. Or if we add this kind of chain here, saying, okay, the concatenation of is-sibling and has-son introduces a new relationship, then you will have this new relationship in your graph. And that is something which should be just there. The idea is to bring knowledge more closer to your data, as opposed to implement this in the application logic of each application that uses this data. And the point is, if you exchange this schema with this data, this should be there just by delegating this task to the underlying reasoning engine. So to sum up a little bit, so in my understanding, an RDF graph consists of two parts: a schema part and a data part. The data part is the data of your domain. It is the object of the queries you currently do. It may contain inferred facts. Hopefully it does. And it's typically larger than the schema and more subject to updates than the schema. So if you query this graph here, then you typically, and you could use SPARQL, for instance, then you typically use schema vocabulary within your query. You rarely use objects of your A-box, because you typically use the schema vocabulary, but most tools offer poor support for users writing SPARQL queries. One exception is the YaSGUI SPARQL interface. Probably you all know that, and it's used for the Wikidata querying. It offers this nice kind of auto-completion functionality and search functionality. So it uses this cryptic IRIs, but you always can search for some terms, and then it offers you kind of the right relationships here. So there's a relative relationship, which is called, I don't know, I can't read it, P1038. But it does not tell you whether this is a sensible relationship at this point in your triple pattern. It does not tell you, okay, you can have relationships between persons and not between cars, for instance. There's a tool which is more helpful in this respect. It's called SPARQList, and it does not rely on the pure SPARQL syntax. Instead, it has a kind of a controlled vocabulary, natural language interface where you can write your queries down, saying, for instance, let me see if I can, oh yeah, I have it here, but I can't see it on my screen. You can see, okay, give me every person which is in kind of SPARQL a type triple pattern, say X, some person, and here I can search for relative, and then it offers me some property here, and if I click on this, then you see also your result view gets updated. Now you query for two variables, so to speak. First one is the person, and the second one is a relative, and then the all other suggestions are updated just because of the focus of this. If I change the focus here or here, then you see all your suggestions are updated according to the underlying schema. Okay. Something which is kind of related to this is faceted search. I mean, that's very well known to even non-experienced domain or users which are not familiar with query languages. You can find it on Amazon or eBay, for instance. Here it's implementation from Oxford University, particularly for doing faceted search on REF graphs. And the nice thing with facets is that you can even do queries that encode logic operators. So people typically know that when they change more than one category within one facet, then it's a logical OR, and when they choose something in a different facet, then it's a conjunction. So they implicitly know what the semantics, what is the semantics of the queries they do. The downside is that this kind of faceted search just focuses on one variable, in comparison to a SPARQL query, so you only see the result set for one of the variable dimensions of your query. You can kind of often switch your context, but you do not get the big picture. The overview is simply missing. So there are other kinds of graph visualizations. This is here one of the most prominent ones, just network visualization, typically force feedback network visualizations. This one here is from Neo4j, but there are others around. I assume that you're familiar with them. Here you can typically start with one node or a couple of nodes and then explore the graph. But the way you can configure your node expansion typically is very poor. You see all the neighbors or nothing. So that's typically often is a mess. When you expand a node that has many connections, then you just get lost in your graph, and it doesn't really keep user orientation very well in this simple kind of network rendering. Something which users often are very happy is, and which uses a different visualization approach, is something we have developed, and it's called Zemspect. It allows for interactive data-driven visualization by grouping of nodes and by aggregation of relationships. So we aggregate things as long as the user didn't ask for details. It allows for selective exploration and sophisticated filtering. And okay, not sure if I'm now able to make it a nice demo. I think I have to just exit this and probably yeah, much better. Okay, so what you can see here is that we have the schema on the left-hand side, so all the classes and types you use in your graph. This is data from the Springer Nature SciGraph linked open data set. So there we have countries, grants, publications, research fields, and so on. And what you can do, you just can drag and drop one of these categories here on the visualization pane, and then you see all the 138 research fields. So each gray dot here is some object of your graph. And what you can do now, if you double-click or click on this plus here, then you see all the other categories which are related to this group of research field objects. So you can go from this research fields to articles or grants, and let's choose grant, and then it shows me all the relationships which exists between this group and potential grants. And if you select one of these relationships, then you see all these 50,000 grants which are related to these research fields. Some of the research fields are now light gray, which means that they are not connected to any of these grants. So the grants are not shown because they're just too much. It doesn't make sense to show 50,000 objects here. So you can check the number of objects to show, but you can in total show just 1,500 objects in one node. But you can look at the grants if you just ask for details here. Then it fetches the detailed information, and you have a list view, and if you click of some of the objects here, then you see the details of the object, which are, in a graph, in an REF graph notion, could be links to literal objects, or are links to literal objects. And now you can go ahead and say, okay, let's look for the organizations which get funding from these grants. And then, okay, let's look at the research field, and let's do a filtering here. Okay, we have two research fields that contain the label economic. Let's check for them and do a restriction. So now I restrict this group here in the beginning, and what you see is that this filtering is propagated through the graph. So we had 50,000 grants before, now we have just about 200. And you see that, that some organizations getting kind of more funding than others. So Harvard University gets 13 grants in this research field here. Okay, that's interesting. Let's do a mark here, and you see all also the highlighting. So if you click here and you go for the highlights, then you see all the connected nodes through your exploration highlighted. And then you can go on. Okay, let's look at the addresses and I don't know the countries. We see okay. The United States is funded most, and then there's South Africa, Canada, and United Kingdom. Let's do a filter here. Apply that filter. And then what we also can do is that we can propagate this filter, saying, okay, propagate this restriction on the address field to the front, and that's indicated by this black triangle here, and it restricts the organizations. What you can also do is to at any time do a parallel exploration or wherever you want. And you can save the whole exploration as well as filtered nodes, which helps you. So let's save this as my grants. And this introduces basically a subclass of grants, and it helps you to refine your schema while browsing the data. And it typically helps people also to find flaws, data flaws. So if you end up at some node which you haven't expected, then either your ETL process is wrong or your schema is not correct or whatever. Not sure what's happening here, but I think I have to wrap up. Okay, so what are our lessons learned in our group? That business critical data is not always perfect, so we always have to cope with data issues, which you find out when you import your data to the schema, or even later by exploring the data. It's not for free, building a semantic model that really covers your domain, but it pays off in the end. That's our lesson we learned. And don't get confused by the triple heap. So don't get too close to the triple, and rather abstract a little bit. Look at the schema and the data separately. That helps a lot to understand what's in your graph. And key factors for effective querying exploration is user guidance. I mean, if you don't get any feedback about the schema, you're basically unable to write a proper SPARQL query. I mean, that's what we experience often. If you write a SPARQL query and you get no results, you're not sure whether there is actually no data or whether you have misspelled your query. The visualization should be scalable, so it doesn't help if you're able to render one or 200 nodes. Our data is much larger. And it should keep user orientation and helps the user to interpret what he gets. And it should also be data-driven. And that's it. Thank you.
Thank you so much, Thorsten. Are there any burning questions about the triple heap? I think that's hilarious, but it's true. Before we head into lunch, any burning questions? We're all blown away by the graphics. Great. Okay, so we're about to go into lunch. Before we do that, I have two quick announcements. One, the Lightning Talk sign-up board is right over here. It's got 3 brave souls that have signed up. You should sign up. So please do put some Lightning Talk proposals up over there. And then for lunch, we need you guys to be back here at 13:45. That sounds weird as an American. But we're going to be starting promptly at 1:45. So get your lunch, chat, ask questions, talk about the cool stuff, and then be back here. All right, thank you.